Imagine trying to solve every problem by activating every neuron in your brain, all at the same time. That's what early large language models do. Every token, every layer, and by activating every parameter. It works, but it doesn't scale forever. But what if intelligence didn't require using everything all at the same time? What if a model could choose which parts of itself to think with? That question led to a mixture of experts. Traditional transformers are dense. Every input flows through every layer and touches every parameter. As models grow larger, computation grows with them. More parameters means more memory, more flops, more cost per token. At some point, scaling becomes impractical. Mixture of experts break this assumption. Instead of one monolithic network, the model is split into many experts. Each expert is a smaller feed-forward network with its own parameters, but only a few experts are active for each token. This changes the scaling law. You can dramatically increase total parameter count without increasing computation per token. The model becomes sparse. Let's look at where mixture of experts or MOE fits in the transformer. Attention stays the same. Queries, keys, values, they're unchanged. The change, however, happens inside the feed-forward network. Instead of one feed-forward network, we now have many. So for each token, a small neural network, let's call it a router, decides which experts should process it. The router looks at the token representation and outputs routing scores. From these probabilities, the model selects the top k experts, often just one or two. Those experts process the token. All others remain inactive. This is the heart of MOE. Many parameters exist, but only a small fraction are used per token. That is how models like switch transformer reach trillions of parameters without trillions of computation. And that will have a big difference on the computational cost. But this creates a new problem. What if the router sends everything to the same expert? That expert becomes overloaded, and others, of course, are inactivated and they are wasted. This is called expert collapse. To prevent this, MOE models add load balancing losses. Those losses encourage equal expert utilization. It helps to diversify the routing decisions. The router is trained not just to be accurate, but to be fair. You may ask, what would be the intuition? Each expert specializes. One might become good at, for example, syntaxes. Another can be good at math or code, or another at dialogue. But this specialization is not hand designed. It emerges. Experts learn whatever patterns the routing mechanism repeatedly sends to them. This is why mixture of experts works so well. The model doesn't get bigger. It gets modular. Different parts of the network learns different skills. There is also another benefit. Because only a few experts are active, MOE models are cheaper to run than dense models with the same parameter count. But there is also a trade-off. MOE models are harder to train. Routing introduces discontinuities. Expert imbalance must be managed. Communication across devices become more complex. MOE often requires careful initialization, specialized optimizers, and also distributed systems. This is why MOE is common in large-scale industrial models, but less common in small research setups. When it works, it scales better than dense models. When it fails spectacularly. Another important detail is that MOE doesn't increase per token intelligence. Each token still flows through a limited computation path. What MOE increases is capacity, which is the total knowledge the model can store. This is why MOE models are often excellent at breadth, many tasks, many domains, but sometimes weaker at fine-grained reasoning. MOE also interacts naturally with long context systems. Infinite attention manages memory over time. MOE manages capacity across parameters. Together, they attack two different scaling bottlenecks. Modern architectures increasingly combine three things: dense attention, sparse experts, and long context memory. This is not accidental. It reflects a deeper idea. Intelligence scales better when computation is selective. By now, you may have some idea that there is a similarity to our brain. Biological brains do this. Not every neuron fires for every thought. MOE brings that principle into transformers. So what you hear that a model has hundreds of billions or trillions of parameters, it doesn't mean all of them are active. It means the model has many specialized tools and uses only the ones that it needs. It raises also another question. If attention is selective over token, the MOE is selective over parameters, can we also be selective over queries? That leads us to the next optimization. But for now, it's enough for this video. We will discuss this optimization in the next video. If you like this content or want to follow the next topic, don't forget to hit the like and subscribe button. And I'm curious about what kind of other ideas you may have for such kind of optimizations for the large language model. Please share it with others in the comment down below. Until the next video, good morning, good afternoon, and good evening. Bye.